So in this previous assessment, so this was, it says test 3 over here. So in the previous year, this whole section that we've been doing was taught second. So that's why it appears as test 3 here. So that's just in case you're wondering if it is the right material. So the first question, the temperature of an individual molecule is, and then is that the same as the temperature of the fluid that it's in? Is that the same as the temperature of the other molecules of the same type? Is it the same as the temperature of the vessel itself? Is it all of the above? Is it none of the above? Any takers there? Anyone want to choose an answer there? So, in fact, if you think about it, this is something of a nonsense question, right? The temperature of an individual molecule. Remember, temperature is the perceived state of energy, or its temperature is really a reflection of the average kinetic energy in the entire fluid. So when we look at an individual molecule, it's not that we can define anything like a temperature. The concept of temperature disappears for an individual molecule. You can talk about the velocity of a molecule or about the rate of vibration of a molecule, but temperature itself vanishes because it's really about the motion of the molecule. So you can't talk about the temperature of the fluid that contains it. So the concept of temperature of a molecule doesn't really exist. So none of these are valid. And so E would be the answer here, right? So there's no such thing as temperature of a molecule. It's the same as asking what's the concentration of a molecule, right? That's a nonsense phrase. Okay, then for the next one, if your fluid is moving at velocity u and your individual species are ui and the concentration is Ca, then the convective flux of A is. And then, of course, we talked about the bulk velocity. We can define the bulk velocity and we can define the concentration of A, but then this is a different, this velocity is the total velocity, including diffusion and all of that. So that would be the overall flux. So this is the total flux of component A, whereas the problem is asking about the convective flux of component A. So if you want to know the velocity aspect of the movement of component A, then it must be specifically the velocity of component A and the concentration of component A, right? You can also look at this, but XA times U is not the same as UA, right? So that's not the answer either. So for question 2, that's the correct answer there. Then we are asking here about the diffusion flux. So between 2 points, so it doesn't matter what the space is, as long as you can locate 2 points, and then you have the concentrations at those points defined, then we know that the diffusion flux is driven by the concentration difference, so C1 minus C2. You could say, well, don't we always write dc dz? So shouldn't it be a combination of delta C and delta Z? So that is true in the sense of if you want to actually calculate a number proportional to the diffusion flux, but that's not the actual driving force, right? The driving force, remember, these two are arbitrary positions. So the driving force itself is not influenced by your arbitrary selection of position. So you can say your driving force, the one thing you do know is that the driving force is proportional to the difference in concentration, right? So this is an independent variable. And so you can, if you can arbitrarily change this, then you are not going to change the driving force. but the actual difference in concentrations, that does affect the driving force. So that's B. Then we have a two-part question here. So in this one, we are told that A goes to 3B. And so 1A is coming in and 2Bs are coming out. And in this part of the question, right, and it's just giving us this, which we know anyway. So in this part of the question, we don't really need to calculate anything. So we might as well just read this and see if we can answer it. Excuse me, if we can answer it as it is. So here, we can see that there is counter diffusion, right? Number one, neither one is stagnant. A and B are not stagnant. And then there is counter diffusion. So 1 of A and 3 of B. So A is moving towards the surface and B is moving away from the surface. So there is counter diffusion, but it's not equimolar, right? For 1 mole of A coming in, we get 3 moles of B going off. So it's not equimolar counter diffusion. So the first statement, because the fluid is stagnant, and yes, the fluid is stagnant, then it's saying that equals 0. But just because the fluid is stagnant doesn't mean there's no net flux. The net fluid being stagnant doesn't prevent the diffusion that's happening. So the net flux of these two is not 0. And then it says, because the reaction conserves mass. So yes, the reaction always conserves mass. You are not creating mass or anything like that. But that doesn't mean that the sum of the fluxes is equal. So if you want to look at conservation of mass, then you could multiply the molar mass of each of these, and then you also have to multiply by the stoichiometric coefficient, and then you can talk about conservation of mass. But this true statement is not equivalent to this statement, and this is not true either. So these two are false. Then here dxa dx is positive. So x is defined as positive in this direction, right? And that's something that perhaps we didn't spend enough time saying in all our developments. By the way, I'm screen sharing, right? Yeah. So we didn't say enough, or we didn't make enough of the fact that when we define a dimension, we are also defining it in a specific direction. So here, if x is defined as positive in this direction, that means it increases this way, right? You always have to define your dimensions with the direction in mind. It's not just some arbitrary number hanging in space. It's a value that is changing in a specific direction. So if x is defined to be increasing in this direction, then if we look at component A here, we can say that A has a high concentration here and a low concentration here. So your concentration, your mole fraction of A is high here compared with here, because A is being consumed on the surface, right? A is being converted to B. So you have a high concentration of A here and a low concentration here. And so if you think of your gradient dx. So your gradient dxa dx, if you imagine two locations in the space, so let's take xa2 minus xa1 and divide that by the positions x. In fact, it's a little bit unfortunate that it's x because it's a bit confusing. So let's change those to z's instead. Let's say we were looking at dx dz. So that's dx dz, right? So if you take a location xa2, right? So if you imagine some value out here, so maybe it's 10 over there and it's 1 over here. So then it's 10 minus 1, and then Z2 is high here and low here. So maybe that's 5 and that's 0. So it's 10 over 5 and it's a +2. So it's actually positive here. So that's the answer. I can see here I highlighted the wrong thing, but this is actually positive. So your gradient or your dx is positive like this. Okay. So that's the right answer here. C is the answer for number 4. Okay, then the next one, the net flux of A can also be written as, and to answer this type of question, I wouldn't try and how can I say, I wouldn't try to just read these and try and anticipate from this. I wouldn't try and do this intuitively. So I would much rather do the full calculation or the full derivation to get the answer here. So let's do that. So we have A goes to 3B, and then we have our flux balance. So we've got minus C times DAB, and then plus XA, sorry, I must here DXA, and I'm going to just do this in Z, right? Just because it's less confusing. So that's XA, and then we have, of course, NA plus NB. And then this is the part to do carefully to work out the relationship between the two fluxes. So you can see that for every 1 A coming in here, 3 B's are going off there. In other words, the molar flux of B is minus 3 times the molar flux of A, right? Minus because they are in opposite directions, of course. And then 3 times the molar flux of A, because 3 times as much B as A is going off. So we can say NB is minus 3 times NA. And so that's a common mistake. And in fact, even in my solution, I felt the need to write here the incorrect answer is this. And I actually showed the working for the incorrect answer. So the correct way of looking at it is, the flux of B is 3 times the flux of A. So when you read this, don't do it on the wrong side. So if we apply that in here, then we can see NB is minus 3 NA. So you've got a minus 3 and a plus 1. So this is a minus 2 NA overall. So minus 2 times NA. So that's what we have there. And then if we take that across to the left-hand side, then this is simply, we have here a 1 plus. So 1 plus, and then when we take that across, it's going to be a 2XA here. Okay, and then that's pretty much what we are looking for. So here's the form that we'll get, right? If you divide that 1 plus 2XA from this side, if you just divide that through, then you can see that the balance that we'll write is this one. So that's now in the standard form for us to do our integration. Right, so that's the answer we are looking for there. Okay. And then this one is about the diffusion coefficient or the diffusivity. And we know that the diffusivity, it does increase with temperature. So the molecules have a greater kinetic energy as we increase the temperature. And in fact, I should say that the other way around. Temperature is defined based on the average kinetic energy of the molecules. And so, so this is definitely true. And so it is going to increase your diffusivity if you increase the temperature. Then if you think back to some of the correlations that we had, right? So if you look back at the diffusion coefficient set of notes, we had a number of correlations there, and most of them had molar mass involved in that correlation. And we had that diffusivity was decreasing with molar mass. And then we did explain that observed decrease with molar mass as being due to the increased inertia. So if your molecules are bigger, then your diffusivity will be smaller compared with diffusivities for smaller molecules. So B is true as well. And then we did also observe a pressure influence, and that typically occurred in a denominator. So it does also decrease with pressure. So as you apply a greater pressure, then your molecules, there's denser packing, and so that also reduces your diffusivity. So all of the above are correct. So the answer we're looking for here is D. Any questions or comments so far? Okay, now in question 7, it's giving us, oh, thanks, Freedom, you've pasted the link in the chat, so I'll open that up just now. Okay, so in question 7, we've got here the observed molar flux. It's given in this form. So in this case, is this the same as the one before? It's not the same case because that has a, this is a plus here, whereas this one is a minus here. But it doesn't claim that this is related to the earlier question anyway. So it just, if we happen to know that's the molar flux, then what's true here? Number one, we can see it's not in equimolar counterdiffusion, right? If it were in equimolar counterdiffusion, then we would say that Na equals minus Nb. So equimolar counterdiffusion. So Na, this part would be equal to 0. And so we would have an equation simply like this, right? The second term on the right-hand side would vanish, and that's what we would be left with. So the equation is not of that form. So it's clearly not, this is clearly not the case. Then diffusion through a stagnant solvent. So in that case, we would have, so diffusion through stagnant B. That means that Nb equals 0. And if that's the case, then our equation here would become this, right? So, Nb is 0, so we are just left with this. And then if you group that, then you'll get a 1 plus XA. And so you would expect to get here 1 plus XA, which is not what we have. So that's not true either. And then infinitely dilute. So if it's infinitely dilute, that implies to us that XA times Na plus Nb, that's approximately equal to 0, at least in comparison with this term, right? So maybe it's best to write it in full. So let's just say this Na is approximately equal to just this term. So your second term is approximately 0 in this infinitely dilute case. And then again, this is not the equation that we got. So we've got 1 minus 2xa. So it's none of the above, right? So E is the answer for this one. Okay, then yes.
Sorry, sir. Is it okay if I could just see something about that infinite dilute solution? There's something I didn't quite understand.
So infinitely dilute, if we imagine some solution here, and so component A is then a component that's in some medium. And so we regard component B as being the medium. So we've got B, and then A, there might be just a very low concentration of component A in that medium. So there's a very low concentration of A in the medium. So that means even though you might be trying to develop an expression for changes in A, the main molar flux is going to be this one. So your primary molar flux will be diffusion. You do have bulk movement of A, but because A is in such a small quantity, this is not going to contribute much to your total molar flux. So because it's proportional to XA, there's a very low molar flux. In comparison with this one, even though the concentration of A may be low, you might have the case, let's say it's like this. So if you have a high concentration of A here and a very low concentration elsewhere, then there is a sharp gradient. Even though the amounts are low, the gradient might be sharp enough that dxa dz is significant. So in that case, we would say this term is much greater than this term. And so that's the expression that applies. Does that cover it?
So it does. Thank you.
Thanks. Okay, so that's not the form that we saw here. So it's not infinitely dilute either. Okay, then component A is in a flowing stream in a long pipeline. So A is being absorbed onto the wall of the pipe. So this is a case, let's just see, how does that look? No, that's not going to help. Okay, so here's your pipeline, and you have flow in the pipeline. And component A is being carried in here. And component A is being absorbed onto the walls of the pipeline as well. So we are losing component A as we are diffusing through here. A is being lost as it gets coated onto the wall. And the fluid, obviously, the hydrodynamics are that the fluid is flowing here. But the concentration of A, so A is being carried in and out, but it is also being absorbed onto the walls here. So in this problem, we are asked, A is being absorbed, a ring-shaped cylindrical. So yeah, it's even telling you what the control space looks like. And then it's asking about turbulent flow. So it's saying, yeah, you've got your pipe flow, and we can define some areas and so on. So we can define the curved area and the flat end area. And we have turbulent flow. So what's true here? Which of these are true? So the key part of this is that it's turbulent flow. So in turbulent flow, remember if you think about starting at a low velocity, then you have laminar flow. So if you have laminar flow, then your fluid follows that parabolic velocity profile. And so you will definitely have radial concentration gradients, right? In laminar flow, the concentration is going to change with radial position. that's not the case when you have turbulent flow. In turbulent flow, the fluid, as the name tells you, is well mixed in the radial direction. So the gradients in the R direction are approximately 0. And so if we think about the type of curve that we expect, we would typically write terms involving DDR and DDZ. So although I must say the way this is phrased, which is true, you know, it's not untrue to say that the flux in the R direction is this, although, yeah, I mean, you could define this, but it's not relevant. You know, that's maybe a better way to phrase this to say would be to say, which is most relevant. So this may be true, but it's not relevant. These gradients are 0 in the R direction. And also here, you've got a gradient in the R direction. It's not really relevant. What makes it, this is, if this is flux in the R direction, so the most relevant one would be that the flux in the Z direction is proportional to the gradient in the Z direction, and then you have flow in the Z direction. So I would say this is the most relevant expression that you will use in your mass balance. Okay. And then the relevant boundary conditions. So number one, yes, you would anticipate that you would need the initial condition. So in terms of time, and if you look here, the others don't really have, well, this one does have something in time, but we'll see this one doesn't make too much sense. But this is the only one involved with times, and we definitely will need a time boundary condition. So that's one. Then the center line position, that there is symmetry around a cylindrical pipeline. So that is true. Well, even if it's a square pipe or whatever, at the center position, there's no gradient. So that one's also true. And now this is this doesn't look like it makes sense, because we know that at the inlet position, we will have an inlet concentration. So at Z equals 0, this is true, but it's not true for all Z, and it's not true for all time either, especially with A being absorbed on the walls. So the concentration can't be the same everywhere in the reactor. And that's perhaps we should acknowledge that's largely because of A being absorbed onto the wall. And what we expect then, if it's being absorbed on the wall, is we would enter at some concentration, Ca in, and as A gets absorbed on the wall, the concentration of A in the fluid is going to do this, right? It's going to drop over time. If it was not being absorbed on the wall, then yes, you could say A stays at the inlet concentration and it flatlines like that. So in that case, this may be true, but if A is being absorbed on the wall, then definitely that's not true. Then this one is the actual statement of A being absorbed onto the wall. So this is saying that at the wall, we will see some diffusion in the R direction, and the flux there will equal the absorption rate onto the wall. So the only driving force for A towards the wall is because A is being absorbed on the wall. So we can express that as the diffusion flux being equal to the absorption flux there. So we are told it's a first order, A is absorbed. Yeah, it says here first order absorption of A onto the wall. So that's how we express that, right? KCA. So there's a hidden 1 here. If it's 0 order, then it would just be K. If it's second order, it would be KCA squared. So this is a first order absorption flux of A onto the wall. And so that absorption flux must equal the diffusion flux towards that wall. So yes, this looks like a valid expression of the absorption flux. So this is true. So far we've got this could be true. This could be our definition for the initial amount. this is almost certainly true, and this is true. And so far we've got what, 1, 2, 4. And you see this one is also true if the pipeline is long enough, and it says it is a long pipeline. If your pipeline is long enough, well, if A is being absorbed, then it won't be true, right? So, sorry, I'm kind of talking to myself there. If A was not being absorbed onto the wall, then you could say, well, A will undergo whatever changes it's undergoing, and then if the pipe is long enough, it will whatever changes it undergoes will have died out by the endpoint, and the gradient will be approximately 0. But in the case where A is being absorbed all the time, then we just expect something like this, that A is being lost until it reaches a perfect 0. It's just being absorbed all the time. So the gradient is not 0 here. Here, I haven't maybe drawn it well enough, but here we anticipate A could reach a steady state. Here, if it is constantly being absorbed, unless it reaches 0, it's not going to reach a flat line there. So this one, in a way, is debatable, right? In a sense, this problem, not in a sense, in this problem, we haven't said enough. Well, I haven't read it so carefully. Yeah, it doesn't say that A could go to 0. So we could only reach this case if the concentration of A goes to 0. So that's a very special condition. So this by itself, you would have to say and CA equals 0 at Z equals L. So that's the only case when 5 could be true. So it looks to me like 1 and 2 and 4 are correct. So 1, 2, and 4. And in fact, you could also be clever and do this by elimination, because we said this was not true at all. So 3 appears in every other answer. So it can't be any of these 3. So C. But I would say, it does say only here. So I would, this part is kind of, there is a condition under which this could be true. So that's a little bit more debatable. But otherwise, C is the answer there. Okay, any questions or comments on that? Okay, and then the last one. So it's asking about the same problem, and then it's asking what is the expected solution. So let's see which for the problem described in 8. Yeah, this problem. So if we look at this, A is entering and then it's being absorbed onto the wall. So A is not coming in at 0. A is coming in at some non-zero value. So first off, if we look at all these graphs, A starting at 0, it doesn't say A is 0 anywhere here. What we can say is that A concentration is going to drop. See if which correspond to the expected solution. So here A comes in at non-zero. So I would say in this case, your A concentration, if we were to sketch out some possible situations, A would start out somewhere like this, and then as time goes on, so there is a steady state, and initially it may take some time for us to develop to that steady state. So it could be the case that initially we did not have any of A in the reactor. So right when we start this, if it's the case that CA at T equals 0, for all Z positions equals, and we define that as CA naught, but if that equals 0, So if we didn't have A in the tube initially, then our starting position would be here. So we would start with that as our A concentration. And then as time goes on, the concentration will rise here. So as A enters the reactor, then the A concentration starts to rise. And it would be more like that initially. And then as A actually convects, into the reactor, oops. So as A convects into the reactor, then its concentration does rise. And then it will reach some steady state. And it will never reach its inlet value because A is being consumed steadily, but it will reach some steady profile. So that's what we expect to see. And if you look among these, in the first case, it's saying fine, A enters, A is 0 initially, and then it enters, and then the concentration rises, and eventually it's at the inlet concentration. So we know this is not true. A is being absorbed, so it can't reach the inlet concentration. Here, it's saying the same thing, just that it goes through a different transition. And A can't drop like at that kind of gradient. Even if it did go to the inlet concentration eventually, it wouldn't drop like that. And then this case here looks like the most realistic. It rises, but then it reaches a steady profile, which is not a flat profile. And then it's not these cases. So here, it's not the case that we started out with a certain amount of A in the tube and then it dropped and we reached some concentration profile like that. Especially here, it's a rising profile. I mean, here it's dropping for some reason near the inlet, and there's nothing to suggest that would happen. And then there's no reason to suggest that it would rise and as we go down the tube. So definitely this makes no sense. Here also, there's no indication that A would rise. So these two are out. So this is the one we expect. Okay, so that's the first part of this problem. Let's have a look at the Publon. Okay, and so Freedom, the one you want us to look at is this question 1, is that right? So of course, we can get the complete solution here, but let's just look at it from scratch. So you've got
okay.
Yeah.
Okay, it's okay, sir, but I think the one I was referring to is under concentration profile. But we can look at it also if you're gonna look at that one again.
Okay.
Yes, on that one, sir.
Okay,
yes.
So we'll start looking at it. We're almost out of time here, 4 minutes left. So let's start looking at it and then we can continue on, I think it's Monday. So
okay.
Here we've got your A forming B, and that's happening at a high rate on the particle. Your particle radius is given, the total concentration, and that's in the bulk fluid is given, and you have a diffusivity. So A at a distance of that from the particle is measured, so that's known. And we want to know the molar flux of B. So first off, this part you can do without deriving the full setup here, because if this flux is due to the particle, so let's just sketch it here quickly. So we've got our particle, and we've got A traveling to the particle. So A is traveling to the particle, and that's at the rate of 100 moles per second per square meter. Is that right? molar flux is 100 moles per second per square meter. So that's what's coming in here, 100. And then B going off is going to be 2/3 times that. So let's look at that. So B, so let's think about here, which one is faster. So it takes, so 3 A's come in and 2 B's go off, right? So the leaving rate of B is less than the entering rate of A. So it's going to be 2/3 A. So we can say NB equals, and it's in the opposite direction. So it's minus 2/3 NA. So minus 2/3 times 100, and then that's going to be our flux of B. That's strange. I don't seem to have that answer available. Let's see what 2/3. So it is that. Oh, molar flux of A is 250.
Yeah, that's why I'm confused, like how we got that 250. Yeah.
Oh, thanks. Yeah. Yeah, so it's given the wrong, by now this question has changed here, so it's not showing anymore what was shown there, but it was showing 100. So there's an error in this problem. Thanks for that. This needs to be fixed. Yeah, so actually it was supposed to show 250. So 250 times that 2/3, then you'd get that answer. Thanks for picking that up. Was that the source of? Yeah.
So in short, we just have to take that NA given. So this one was an error. We just have to take that NA given. For example, we're given 100 on that question. We're just supposed to say -2/3 times 100, then get the answer.
Yeah, that's right.
Okay. Okay, thank you, sir. That's where I was confused, sir.
Okay, thanks. Okay. So then we can come back to the other questions here, but for this one, just you can keep going with this problem. Don't look at the solution, right? Because when you have the solution available to you, when you browse, look through a solution, it looks very easy and you assume that you know everything, but there will be some step where you'll get stuck. So always when looking at a problem and trying to understand the solution, work it out first, see where you get stuck. When you browse, look through the solution, it will always seem to you like, yeah, you would have done all of that. And so you won't pick up the places where there's a gap. Okay, so work through that. We can continue with this problem on Monday. And that's it for today.